Okay, so the internet connection was lost. Okay, so we have basically based on why we have a binary hypothesis, and we say that which hypothesis is true, and that we say on the basis of the signal that we have received at the receiver end, and the signal that we have received at the receiver end is y. Okay, so that is basically the background which I wanted to brief about. Now, the question that we have all seen that we have the sufficient statistic and we want to compare it with the threshold value, and we want to know that basically if it is greater than the threshold value or it is less than the threshold value. If it is greater than the threshold value, one hypothesis would be concluded, and if it is less than the threshold value, the other hypothesis would be concluded. On the basis of this, we are basically making this hypothesis detection problem. We are basically solving this. But the question here that comes is that how do we decide this threshold value? How do we decide that what is the value that we have to bring here so that with which we can compare this sufficient statistic and conclude to a particular hypothesis that we want to decide. So the mechanism basically proposed to know the value of this threshold value, that is essentially covered in this lecture, and that was essentially given by the Neyman Pearson law, and that is what we are going to see now. So we'll look into Neyman Pearson rule or the theorem and so on. So basically now let us take a particular case that we have this received signal, and that is equal to U plus W, where U was the transmitted signal, W is the AWGL version noise. And we say that either 0 or 1 was transmitted. Either 0 was transmitted or 1 was transmitted. So that means that U is equal to 0 or U is equal to 1. These are the two cases that we are having right now in front of us. And when U is equal to 0, this case now basically we have to formulate a hypothesis from our side based on the observation Y. We have to decide that which was the symbol that was transmitted, which was the value that was transmitted based on the received signal Y. So our hypothesis that we will be formulating from our side will say that either U is equal to 0 or U is equal to 1 was transmitted. So we'll say that if we are deciding that U is equal to 0 was transmitted at the transmitter end, hypothesis H0 essentially signifies that U is equal to 0 is transmitted, has been transmitted at the transmitter end, and hypothesis H1 signifies that U is equal to 1 is transmitted at the transmitter end. Okay, so this is the case. Now we have here essentially we have when I write this, you can see that Y is equal to U plus W, where we have this W is distributed with a normal distribution. We assume that, let us say that it has a mean of 0 and a variance of 1. It is a standard normal. W, additive white Gaussian noise, is a standard normal distributed random variable. And further, we would be having two cases where we will be having under the H0 hypothesis. Under the H0 hypothesis, we have U is equal to 0, that is transmitted. So we'll have the received signal that would be comprising only of the additive white Gaussian noise. And the H1 hypothesis, when we have here, so the H1 hypothesis will consist of U plus W that we have with the eraser. Okay. So this is essentially 1 plus W. Okay. So corresponding to this, Y will have, corresponding to the H0 hypothesis, Y will have a PDF that is standard Gaussian only, because we have Y exactly as the relative white Gaussian noise, and corresponding to the hypothesis H1, Y will have a PDF that will be distributed with mean 1 and variance 1. Okay, so these are the two cases that we are having here. Okay, the other way of saying that, because a general distribution of Y, the general distribution of Y is mu sigma square, where sigma square is already equal to 1, that we already have. Here mu is a mean, and mu, this zero mean signifies the H0 hypothesis, whereas the mean 1, in the other case, when the signal is present, when the signal 1 is present, the value of u is 1, that time we have hypothesis H1 true, and in that case the mean of Y will be assuming a value 1. Okay, this H0 hypothesis, further we need to know that we'll name it as null hypothesis, a null hypothesis, and the H1 hypothesis we name it as the alternate hypothesis, the alternate hypothesis. Okay, so this is the case. Just a minute. Okay. Every time we are going to have a new document only, or what? It's better. Yeah. So now we are having basically share this document. Okay. So we have this. Now we have basically I'll rewrite the case that we have mentioned here, that the mean of the signal Y that is equal to having a value 0, and that is signifying the hypothesis H0, that is null hypothesis, and the mean of the signal Y is having a value 1, that is signifying the H1 hypothesis, which is known as the alternate hypothesis. Okay. Now, basically, our aim to decide that which hypothesis is true is essentially about deciding between two probability density functions. Okay, the first probability density function is Y following Gaussian normal with mean 0 and variance 1, and the other Gaussian distribution, the other hypothesis signifying the Gaussian distribution with mean 1 and variance also 1. So basically we have the first PDF that we are drawing. We can see that we have the mean value 0 here, and the standard deviation is and the variance is 1 here. And the other hypothesis that we have right now, the shape is slightly not very proper, but this is a Gaussian distribution only. So this here we are having basically the value 1. Okay, so we have this mean value 1 here, and you can see that basically this peaks at the mean value 1, and here, so this particular probability density function, this is signifying to R H1 hypothesis, and this is signifying to R H0 hypothesis. Okay, this is the case. Now, when we and we have to decide between, our aim is to decide between these two probability density functions. Okay, our aim is to decide between these two probability density functions. Okay. Now, if I say that which one of the suppose we are having value, I say that we have here the received signal y, and this received signal is received in a span of time. Within a span of time, we have various samples of this received signal. We have y0, y1, and up to, let us say, yn minus 1. We have all these received samples, and similarly, we have, for an example, suppose if I say that what is y0, so y0 is going to be u0 plus w0, and so on. Okay, so I'm saying that suppose I have received one sample value y0, and based on this y0, I want to decide that which of these probability density functions are going to be true. Okay, so which of these probability density functions are going to be true? What I have in my hand, at my hand, is simply this y0. Okay. Okay. Now we have this. Yesterday we had seen that one way to decide the threshold value. Now, essentially, what I'm going to do is that I'm going to compare this y0, this received signal value, to a threshold value. And if it is greater than this threshold value, I will decide that hypothesis H1 was true. And if it is less than the threshold value, I will decide that H0 was true. So let us take for a very simple case, very visible case, that the point at which these two PDFs are intersecting here, this will be simply be 1 by 2 here. Okay, this value will be 1 by 2. And I say that if y0 is greater than 1 by 2, let us say that my received signal y0, if it is greater than 1 by 2, we will conclude that u is equal to 1 was transmitted. U is equal to 1 was transmitted, which is the other way of saying that H1 is 2. Okay, and likewise we have the other case. Okay, now when we say that, okay, we have said that here we are having the threshold value we have here as 1 by 2, and on comparing with 1 by 2, if y0 is greater than 1 by 2, now we can see here, let us say that in actual case, H0 was transmitted. Okay, let's consider a case that H0 was transmitted in actuality. But what I obtained here was that y0, y of 0, this signal sample is having a value, let's say something like 3 by 4. Let us say this is 3 by 4, which is greater than this 1 by 2. So this is lying somewhere here. Now this is the value. I'm having this y0 as 3 by 4, and which is greater than 1 by 2. So what I will be deciding? I will be deciding that since it is greater than 1 by 2, since y0 is greater than 1 by 2, so since y0 is greater than 1 by 2, H1 is 2. Whereas in actuality, H0 was transmitted. Okay. So the probability of deciding H1 as true when H0 was transmitted in actuality. Okay, that is, I define it as the probability that of deciding H1 when H0 was transmitted. Okay, this probability is known as the probability of false alarm. Okay. On the other hand, this event, the event of that the event of deciding H1 when H0 was transmitted is called type 1 error. This is an erroneous event. Okay, actually H0 was transmitted and we have decided that H1 is transmitted. So basically this condition can be seen as a false alarm condition, that actually H0 is signifying the value 0 that was transmitted, whereas we are saying that 1 is transmitted. So in actuality there was nothing, there was just 0, but we said no, there is some value, there is one value. So that is basically a false alarm event, and this is known as a type 1 error. And we can see here that there is a probability. Suppose we have this 3/4 here. So we can see that, okay, there is a probability that basically we are having there's a probability of both the making both the decisions. We can say that okay, H0, this is lying within the PDF H0, but there is also a probability that is coming into this H1 region. Okay. These probability values, when we find out the area of this continuous PDF, this is lying in the H1 area, in the H1 region. Okay, so this is essentially we name it as this red part as the type 1 error. Okay. Similarly, we have the other error, and that is known as the type 2 error. And that says that, suppose, let us say that in actuality, let's say that in actuality, H1 was true. That is, we say that, suppose H1 this was transmitted as a wrong term. This is basically was true. Okay, H1 was true, oblique, you can say that U is equal to 0 was transmitted. And similarly here also, H1 is true, and I say that U is equal to 1 was transmitted. That is what the case right now we have. So, which means that, let us say that if I have any value, let us say that I'm getting a value y of 0. Y of 0 is, let us say that less than 1/2, and that is when y of 0 is equal to, let us say, 1/4. So when it is 1/4, when y of 0 is less than 1/2, we'll directly conclude that H0 hypothesis is true. But in actuality, H1 was true. So this is another kind of event, and this particular event, that when H0 was decided, whereas H1 was true. Okay, so this event that H0 was decided, but H1 was true, this particular event is called, this event is called the type 2 error. And the probability of this event, okay, the probability of this event. Basically, there's a type 2 error, also called a misdetection event. This is a misdetection event. Okay, so the probability of this event, if you want to see, the probability of this event is called the probability of misdetection, denoted with P subscript MD, and here the probability of false alarm, this is denoted with P subscript FA, false alarm probability. Okay, so these are the probabilities that are associated with these type 1 and type 2 error, and we can see that this particular part is signifying me the, because in actuality H0 was true, whereas this part, this area, is telling me the probability that we are deciding that in actuality H1 was true, but this particular area is signifying me the event that H0 has been decided. Okay, so this is the type 2 error. Okay, now we have basically one thing which we can see here, we can very directly see here that based on this threshold, both these errors are completely based on the threshold value. Okay, based on these threshold values, we are having both these events. Let me see. Yeah. These errors are totally based on the value of the, these errors are totally based on the values of the threshold, and we can see very clearly that these errors can be changed by changing the threshold, can be changed by changing the threshold value. Basically, we can see that if I start increasing the threshold value, so you can see here that if I start increasing this threshold value, suppose if I start increasing this threshold value, the type 1 error is decreased if threshold value is increased. Okay, I can express it in with the help of figure. You can see that I have these two things here. This is 0. This is 1. Let us say that I have a threshold. I fix my threshold value here. This is my threshold now. Initially it was here 1/2. Now I fix the threshold value here. So I can see that the type 1 error will be reduced to just this much region, whereas the type 2 error, that will be basically that would be increasing. Okay, any value which we are having below this, it can have both the probabilities. Okay, so essentially what we conclude here is that both these errors The third important point here is both the errors cannot be reduced simultaneously. Cannot be reduced simultaneously. If I increase one error, if I decrease one error, the other error will be increased. Okay. So this is the thing. Okay. Now here is where the Neyman-Pearson rule comes. So the question that comes up here is that what is the optimal value of the threshold value? Because if I take any threshold value, if I'm going to increase the threshold value, type 1 error is going to decrease and type 2 error is going to increase. If I reduce the threshold value, type 2 error is going to decrease and type 1 error is going to increase. So both errors cannot be reduced simultaneously, that we know. So essentially we have what is the optimal threshold. Okay, so that is answered by the Neyman-Pearson rule. It says that let us fix one error. Fix one error. When we know that we cannot reduce both of them simultaneously, let us fix one error and minimize the other error. Okay, so I'm having here basically I'm having this case. Once when we are at this thing, so you know that the type one error. So basically we are going to fix one error and minimize the other error. How about fixing the type 1 error only? That is, how about fixing this one and minimizing? Okay, so type 1 error we can, this mechanism was basically formulated by Neyman-Pearson, and type 1 error we can see that that is essentially nothing but our probability of H1 when H0 was transmitted. This way we have written. So this is nothing but equal to, suppose we have only one sample here and Y0 is having a value greater than eta, and where we are knowing that H0 was transmitted. Okay, so when I want to write this, you can see that the distribution of Y0, okay, the distribution of, I'm writing a probability term. So I want to calculate from the continuous probability density function of Y0. I have the continuous probability density function of Y0, and from that continuous probability density function of Y0, I want to calculate this probability. So I need to integrate the PDF of this Y0. And when I integrate the PDF of this Y0, I can see that this will be having root 2 pi because sigma square is 1. And we have exponential and minus exponential to the power e to the power minus of, let us say, the variable is z square, mean is 0. Already we have here mean 0, dz, and this is going to vary from eta to infinity. This is essentially my probability of false alarm. This is my probability of false alarm. So I have my probability of false alarm here, and you can clearly see that this is coming out as a Q function of the threshold eta. Okay, so I get this probability of false alarm as a Q function of threshold eta, and the other thing now we have here. Okay, the next thing we have here is that what we want is the as per the NP criteria, Neyman-Pearson criteria, that we want to fix the probability of false alarm and minimize the probability of misdetection. Just remember that we are going to minimize the probability of misdetection. That is nothing but the probability that when H0 was transmitted and H1 was decided, that probability. And we write this optimization problem with a constraint that subject to, we have this probability of false alarm having a fixed value. So this probability of false alarm that is having a value, sorry, I'll return it the other way around. This is my probability of misdetection and this is my probability of false alarm, and that should have a fixed value alpha. Okay, essentially I'm going to minimize this PD and with a constant on the probability of false alarm that should have a fixed value alpha. Okay, this is what I'm going to do. PMD. Okay, now you can see here that when we are writing this PMD, that is the probability of misdetection, this is essentially the probability that H1 was transmitted, whereas we have decided H0. You can see that this is nothing but 1 minus the probability that H1 was transmitted and H1 was decided. Essentially that. So this particular event that H1 was transmitted, H1 was true and H1 was decided. H1, this particular event that H1 was true and H1 was decided. This particular event is called detection or correct detection. Basically, we directly write it as detection, and the probability that is signifying the probability of this particular event that H1 was transmitted and H1 is true is known as the probability of detection PD. We know that PMD is P H0, that is 1 minus probability H1, and we have here basically the probability of misdetection is 1 minus the probability of detection. Okay, so when I'm writing that I want to minimize the probability of misdetection, that is equivalent to maximizing the probability of detection, isn't it? And the Neyman-Pearson criteria is modified to maximization of the probability of detection with a fixed value that is subject to the fixed value of probability of false alarm. Okay, so this is the thing. Now we have basically let's see that how do we solve this criteria. Okay, let's say with the help of we'll try to solve okay, so this is a very rough way, a very abstract way of understanding the Neyman-Pearson criteria. What the Neyman-Pearson theorem says, okay, we'll look into that because ultimately we want to make the decision on the sample, why not, and that we have to basically decide here. So we'll coming quickly to the Neyman-Pearson theorem. Quickly to the Neyman-Pearson theorem. What the Neyman-Pearson theorem says is to maximize the probability of detection for a given probability of false alarm, that is alpha. Decide hypothesis H1 if the likelihood ratio And how do we define the likelihood ratio? So that is the probability of this received signal y, the likelihood probability of this received signal y with the hypothesis h1 divided by the likelihood ratio of the received signal y with the hypothesis h0. This is greater than our threshold lambda, threshold eta, and where this threshold eta, where threshold eta is found from, how do we find this threshold eta? The essential part is how to find this threshold eta ultimately. When we are trying to do this, maximize this, our objective is to find out this threshold theta. Okay, so the threshold theta is found out from the probability of false alarm that we already have. Essentially, this is the probability of this received signal when in actuality S0 was transmitted. Received signal is denoted by the variable y, and we have this limit y, the variable is y, and here basically this integration will be performed over the values of y. Okay, those values of y over which this likelihood ratio is greater than the value of the threshold. This is essentially integrating this probability, this joint probability, over the values of y, where this likelihood ratio of y with h1 divided the ratio, that is of y with h1 and of y with h0, this likelihood ratio, when it is greater than theta. So the values of y corresponding to this region, for those values of y, this integration will be performed over those values of y. And this we have to fix at a value alpha. Okay, so we essentially need to first perform this. We need to fix this, find eta from here. And once we find eta from here, then we need to find out the probability of the detection. Okay, we'll do one example, and that example will make things much clearer. Let us say that I have been given a fixed value of the probability of false alarm as 10 to the power minus 3. Okay, so let us calculate the likelihood ratio, and the likelihood ratio will be the joint probability of the received signal with the hypothesis h1 divided by the joint probability of the received signal with the hypothesis h0. So this will be 1 over root 2 pi exponential, and I have here minus 1 by 2. Now here we have the hypothesis h1 present. So when hypothesis h1 is present, that time the mean of y is 1. So we are considering only the 0th sample. We have this square here, and this divided by 1 over root 2 pi. We have exponential 1 by 2 and y square 0. We have this kind of ratio we are having here. So now this ratio, this likelihood ratio, this has to be greater than eta. That is what we have said. Okay, so now basically what we get here, when I take this exponential in the numerator, so you can see that I can get here, we have this exponential minus 1 by 2. We have y square 0 minus 2y 0 plus 1, and we'll have minus y square 0 that is coming from the denominator, and this has to be greater than eta. So finally what I obtain here is exponential y of 0 minus 1 by 2, and that has to be greater than eta. Okay, so now this particular event is the false alarm event, isn't it? This particular event, if I'm this particular event, if I'm taking this under the condition that S naught was transmitted, okay, this particular event, whatever I have obtained, let us write it in, the next line to avoid any confusion. Basically, we have, this is an event we have that the likelihood ratio, the sufficient statistic, likelihood ratio is greater than eta. That means that we are making a decision H1. This event says that this is the event of making decision on H1. And suppose if I say that in actuality H naught was transmitted, the same thing, the probability of false alarm this is this. So what would be this probability of false alarm look like? This is the probability of false alarm that H naught was actually true, but we have decided H1. So how are we going to decide H1? When this event is going to be true. So we have this exponential y naught minus 1 by 2, this greater than eta, and this having a the probability with H naught even. This is essentially my probability of false alarm, and that value has been fixed at 10 to the power minus 3. Okay, so now for this we need the for making this calculation we need the PDF of y naught minus 1 by 2. Okay, and that will be difficult. Okay, finding the probability or the PDF of, we can solve it with the PDF of y naught minus 1 by 2 also, but we can make certain mathematical manipulations. Let us take in this expression exponential y naught of y naught minus 1 by minus 1 by 2 greater than eta. Let us take log on both the sides, or the natural logarithm. Let us take log natural logarithm on both the sides. So let us first make this eta as some as the, let us say this eta is going to be some exponential beta. Okay, so when I take this log on both the sides, I get this y naught minus 1 by 2 is greater than beta, isn't it? So I have my y naught is greater than beta plus 1 by 2, okay, which is nothing but log n plus 1 by 2. Okay, now this is my event. This is the event. See, I started with this likelihood ratio getting greater than eta, and now I have converged this to y naught. I am now simply concerned with y naught here. I have only this y naught. If my y naught is greater than ln eta plus 1 by 2, I'm going to decide H1. Okay, H1 is decided. Okay, so let us define this. Let us define this. So let us define this particular factor as eta dash. So I have my condition simplified to y naught greater than eta dash. Whenever I'm going to have y naught greater than eta dash, that time I will be saying that h1 is decided. Okay, so h1 is decided. Again, coming back to the to my formulation of probability of false alarm, and my probability of false alarm again says that the probability of deciding h1 when in actuality h0 was transmitted, and that is basically the probability that of formulating h1 is signified by y0 greater than eta dash, and I have this h0 here. Okay, simple probability I'm having now. I need to simply substitute this probability. I need to put this threshold value in the probability density function. I need to integrate the probability density function over the region which is required here for y0 under the hypothesis h0. Under the hypothesis h0, y0 is having a value, y0 is having a mean 0. So we have a 0 mean, and the probability density function of y0 is 1 over root 2 pi. I have here exponential, and I have here now, I have y naught, and the hypothesis h0 is true. Okay, so better to take another value, another variable here, because we are going to integrate it. Okay. Since we are going to integrate it, so let us take this exponential of z, and the mean here is 0 because we have a h0 hypothesis. So z is square by 2, and I'm going to integrate this over this eta dash to infinity, because this is y0 greater than eta dash here, eta dash. So this is essentially my probability of false alarm. And when I look at this probability of false alarm, now this is clearly a q function of eta dash. So I have my probability of false alarm q as my q function of eta dash, and that we have fixed at 10 to the power minus 3. So if you look into the q table, you will see that the value of q of 3 is something like 0.00134990 and so on. So let us include that eta dash is equal to 3. That is our optimal threshold. Once I have this optimal threshold, I can obtain the probability of prediction from here. Okay, so this is about we can further the value of PD can be obtained by substituting the value of beta dash. Okay, so first we can find out the value of beta, and then we can find out the value of PD. So this is all about the Neyman Pearson criteria. It has got essentially got 3 steps, where we need to first fix the probability of false alarm, then we need to see the likelihood ratio. What we had done, whatever we had written in this theorem here, the same steps we have followed in this example also. So in the first step, we are basically fixing the probability of false alarm, and then once we are fixing the probability of false alarm, then after that we basically find out the likelihood ratio here, and once we find out the likelihood ratio, we try to, from the likelihood ratio, we try to transform ourselves to the value of y0, the region of y0 where this likelihood ratio is lying. And once we are able to obtain the value of this the region over y0, then we simply put the criteria of probability of false alarm, because here this probability of false alarm is written as the values of y, those values of y for which the likelihood ratio is greater than the threshold. So we are essentially doing the same thing here in the numerical also, that we found out the value of which is the region where the likelihood ratio was greater than the threshold, And for those corresponding values, we obtained the corresponding region for y. And once we found the corresponding region for y, we integrated this particular probability density function over those corresponding region of y, now that corresponding region of y, and then we were able to find out the value of theta. Okay. So that's all for this class. Thank you. Thank you.